We continue with Cees from the Land, modern and ancient biosignatures in sabkha-associated microbial mats. Thank you.
Very well. Back into the light, out of a dark sinkhole, back to the surface. I've been told to point in that direction. Let's see. Right, so I'd like to talk about these sabkha-associated mats we find along the coastline of Abu Dhabi. So these are the people I'm working with. There's a large team of Newcastle also present here. Kirsten and Louisa have posters. Andreas from the PI is here as well with a poster. Angie is here as well. And two MSc students, Tom and Guy, who did most of the work. And Martin and Ian at Newcastle and Stephen at the PI. So there's a collaboration between Newcastle University and the PI. We've been visiting there a couple of times, either taking samples with us or, and that's quite unique, taking samples there and immediately analyzing them in their labs without first taking them home and have some sort of diagenetic overprint over our samples. Right. Slightly different talk than a lot of the talks before. I'm not going to talk about microbial textures. I'm actually going to talk about a little bit about the organic geochemistry of these mats. And the main reason Newcastle University's got a big history in source rock research, and in the Jurassic petroleum system of the Persian Gulf, it is believed that the source rocks are basically these sabkha-type microbial mats associated with evaporitic sediments, encapsulating the organic matter, preserving the organic matter, dragging it all the way down, and forming kerogen and expelling hydrocarbons out of that. So how can an investigation into modern microbial mats help me understand the lateral variability for hydrocarbon source rocks, and how can I apply that to the Jurassic petroleum system? I'm not an organic geochemist by background, so I'm more of a texture person. So this was a first attempt to try and interrogate these rocks, not just on the textures, but also on the organic geochemistry. Right, so here we are along the coast of Abu Dhabi. We have these Persian Gulf here in the north, these barrier islands, a lagoon, and these sabkha evaporites here on land. And in between there, we have these kilometer long and about 1.5 kilometer wide zone of microbial mats forming. If we zoom in a little bit more, we can take a transect. And if you look at the microbial mats, well, the non-existence of microbial mats in the subtidal zone here are all reworked. So it's probably all reworked material from further up. And here we have a zone between these two lines where we have intertidal, these polygonal mats. Lots of research has been done on these. And we also find within this intertidal zone, we find these intertidal ponds, intertidal pools, with mats growing there as well. Not a lot of research has been done on those yet. So that's Andreas' work, where instead of having a daily bi-daily exposure in the tidal zone, these mats are constantly submerged and actually have sort of unlimited accommodation space to fill up all the way to the rim of the pool, especially along the sides of the pool. They're sort of building in towards these pools. Yeah. So I'm also going to show some samples from there, some analysis from there. So further up the intertidal range and the subtidal bit of the tidal system, we see these pustular mats, and further down we basically see the evaporites at the surface. If we then take some cores, so this has been work of Kirsten mainly, we can see that in the intertidal zone at the surface we have microbial mats, while further down at the surface we have these evaporites, these gypsum and anhydrites, and we only have buried microbial mats. These sediments, not our core, but other cores have been dated, and there have been progradation rates have been calculated on how this system is evolving over the last approximately 2,000 years. So yeah, So it's surface mats and buried mats, and further away to land, we only have these buried paleomats. So these are the locations I'm going to look at. A little bit dark, I see. So location 1 is too far into the water. We're not going to talk about that today. Location 2 is in the lower tidal area. Location 3 is in the mid. Location 4 is in the upper intertidal part. And location 5 is actually this buried mat. And location pond, the pond location is basically within this mid-intertidal range, a pond sample. So surface water salinities, as expected, are lowest near the open sea and highest towards land. And these buried mats, actually, the pore water show very high salinities and even higher in some other samples, some other pore water samples. So this is an example of these buried microbial mats. So this is location 5. Again, evaporites at the top and 2 sections of buried microbial mats. This is approximately, approximately 30-40 centimeters in thickness. So these are about 15 centimeters each with a gypsum layer in between. Right, so if we then purely look at the intertidal polygonal mats at a surface sample from there, not only did we do organic geochemistry, there's also someone there's also someone taking samples to look at the SEM. So this is again Kirsten's work, and we can see this is a bit texture. Here we have a sample freshly from the field, directly within, I think, 2 or 3 hours taken from the field, sliced up and put under an SEM. And we can see here some filaments in between layers getting apart a little bit, and some other microbial filaments in there as well. More work is done if we then, across this approximately 9 millimeter transect, if we slice this up in about 2.5-3 millimeter slices, and we then do some microbial community analysis. So this is Louisa's work, who then discovered that actually in the upper, I don't know if that's readable. This has 5, I think. Yeah, I can't read it here. Actually, it's easy to read there. So only in the upper 5 millimeters we find some cyanobacteria, and if we then go even more detailed, so at class level, we can see that these bacteria are dominant in the first 8 millimeters, and in the deeper layers we have more sulfate reducing bacteria. So there's a relatively low. It might be just this one sample, we don't know, we're collecting more samples, but it's actually quite a low percentage of cyanobacteria actually at the surface. My biomarker data will actually contradict this. Right, so again, we're looking at modern samples, and then we're going to look at some fossil samples for the Jurassic petroleum system and see if we can compare these two. Just simply looking at the total organic carbon. So again, these are the sampling stations in the lower tidal zone, mid tidal zone, where we have these tidal ponds, and then the upper intertidal zone, and then here we have the sabkha, and here we have the Cees. So this is a combination of basically biograzing here at low salinities, eating away the mets, so low organic carbon being preserved. And probably down here, there's evaporites forming in between, and there's other material being formed, lowering the relative concentration of the organic carbon. So on average, for the surface samples, that comes down to about 2% total organic carbon. But if you compare that to the tidal pond, so that's again from the mid-intertidal zone, but then permanently covered in water, you got a much higher total organic carbon there. And the buried mat shows you that through diagenetic processes, this total organic carbon becomes even less. So if you then look at the free hydrocarbons, so basically the lipids that are available now, we can see that we have a very high percentage of very high volumes of total saturated hydrocarbons in my total organic carbon in the tidal pool mat, and lower. lower in the surface mets and in the paleo mets. So this is your extractable organic matter. If you then look at some of the hydrocarbons focusing on the N-alkanes, I got more biomarker data as well, but I'm not convinced enough by the data yet to present this. So this is the lower tidal zone and the mid tidal zone and the upper tidal zone. So these are all the surface mets, and we can see. So these are not chromatograms. This is not arrival time. This is basically just the percentage of certain alkane chains. So C17 is the dominant chain length. Previous literature showed us a bimodule distribution with dominant peaks at C17 and between C23 and C30. So that's all the previous literature. We don't seem to see that distribution. So based on literature, the peaks in the C17, C22 range are characteristic of cyanobacteria. So cyanobacteria have produced these lipids and these extractable, these available hydrocarbons. But if you then look at, so these are approximately 0.81. So if you then look at so that's again the surface met. So that's the average of these ones. Just specifically looking at C17, you can see again that in the tidal pond you got much higher quantities, and in the buried met they're actually slightly lower, which tells me that these N-alkenes biodegrade with burial and also biodegrade with exposure. Right. If you then look at the monomethyl alkanes, we can see that there are monomethyl heptadecanes available in all samples, monomethyl decanes are indicative of cyanobacteria, so those are present again in all of the samples, and it's only the tidal pond and the buried mets which have monomethyl octadecanes. I'm not entirely 100% sure of the origin of these, but it could indicate that actually these these buried mets don't come from a tidal setting with a daily cycle, but that they come from a more tidal pond setting, that they have been constantly submerged. So that would alter our depositional model quite a bit, but obviously more data is needed to support that. If we then look at the source rock potential of these sabkha-mats, so if we pretend they're going to be buried for a couple of million years and we're producing kerogen, so what we did here is we heated them up to about 500 degrees, so in a rocky wall. Again, total organic carbon, and then my kerogen peak, so the amount of carbon in there which can generate hydrocarbons, and my hydrogen index, if we combine those two in a diagram used by petroleum geochemists, we can see here the S2 peak, so the available the material available to produce hydrocarbons when buried, and the total organic carbon. And we can see that we have especially the tidal pond, but also the mid-tidal samples would form excellent source rocks, while actually the buried met is already degraded so much that it's actually not, well, there's already been quite a bit of diagenesis there. So it's not been in this setting, in the current Holocene setting, this buried met will not be a potential source rock in the future. Again, 1 minute left only. Okay, then I'll go very quickly. Sorry. Oh, there's an orange light there. Good. Right. Good. This is more or less my summary slides. That's fine. So the original goal was to link organic geochemistry of mets with sequence stratigraphy. There's some hint that this tidal pond represents the depositional setting of the buried met. So this buried met in the Holocene setting might not be from an intertidal range, but from a tidal pool. We need some more biomarker data. We're looking at haploids as well, but that data is not conclusive enough to present. So how do we link this to the Jurassic source rocks and reservoirs? We could artificially mature these modern mets to produce some diagnostic biomarkers, or we can look at the Jurassic mets. So very quickly, we have some well data. Unfortunately, I was not allowed to present the sequence stratigraphy of this well data. So this is basically the Arab formation, but then the reservoir, and we've looked at the microbial mets in here and looked at their potential as a source rock, and to see if they come from a similar depositional setting, just based on the biomarkers as the modern mets. So again, we've removed the reservoir oil, and the analysis has only been done on the rock. We've got one indication just in the core, not the best picture, that there are some inclined surfaces, which might indicate that this is actually from a tidal pond and not just horizontal surfaces in my tidal range. So this is basically filling in one of these ponds. That is just a hint. So total organic carbon for the fossil sample. So again, these have not reached the oil window. They're still before the oil window, so this is probably the depositional total organic carbon, not completely degraded. But compared to averages from the modern system, they're quite lower, except for these two samples. And alkyne distribution does show some cyanobacteria origin in the G2 sample. I'm going to skip these. That was too difficult to explain for me anyway, that's fine. Basically, all of my samples, if we just look at S2 and TOC, so again, rocky fault data, they show very low potential to become a source rock, except for maybe this G2 and this G7, so this potential pond sample. So to conclude, very quickly, the main point is here below in the bottom. The remaining source rock potential of the reservoir fossil met is low, which means that do they have a different depositional origin compared to the modern mets, or have they already released their hydrocarbons and are already mature source rocks? The upper thing does not fit. This would not fit our current depositional model. The bottom thing would not. The bottom point would not fit the current burial thermal model for these reservoir rocks. So there's, as per usual, end up with more questions than at the start. Thank you.
Thanks a lot.